Let's talk about something called test for independence. It's one of the probability topics for Stats 1. And I want to emphasize that there are two ways to test for independence. Um, they come from the same underlying algebra of the conditional probability equation. Independence is the opposite of conditional. Uh, Conditional means that if you know something about one event, it changes the probability of the other to be more or less likely. The condition of one thing affects the probability of the other. Independence is, of course, the exact opposite. The condition of one thing has nothing to do with the probability of the other thing. So one of the ways that we test for independence is we simply check the conditional formula and confirm, oh, there's no effect, right? So that's one way. That's the sort of, I'll call it against, right? Against conditional probability. So what we have to do is we have to check the conditional probability formula, right? I'll write that down. The conditional probability of A happening, given that B is known to have happened already, the condition B. Conditional probability is always the probability of the intersection of the two events, always the intersection on the top, right? Divided by the condition, right? We take that intersection and we compare it to the size of the condition, and that fraction is the conditional probability of A happening, knowing that B is given, B already happened. So there's the conditional probability. What we want to do is we want to check it against the probability of the event, right? We want to see if the condition B, right? Conditional probability is asking, how does knowing that B happened affect the probability for A? Well, if we want independence, right? If we want there to be no effect, then we're asking ourselves, does this equal? Does this equal probability of A, right? That's it. That's all we need to know. Does the conditional probability equal the regular probability, the unconditional probability, the probability not knowing anything about any conditions? A lot of different ways to say that. So the comparison we make when we're comparing to the conditional probability, right? When we need to test independence and we know the conditional probability, what we do is we ask ourselves, is the conditional probability equal to the probability without any change? Equal or not? If equal, then we have independence. Simple as that. So what you want to be looking for, in a question you might be asked is something that gives you probably maybe the probability of A, the probability of B, and some kind of conditional probability. If they give you a conditional probability, check it against the probability of that event A. If the two are equal, independent. If they're not equal, dependent. Simple as that. That's so when you, right? So what you're looking for is that the given conditional probability, right? Let's say they give you the intersection and they give you the probability of B. You make that computation and then you conclude, nope, it is or is not equal to the conditional probability. So what you're looking for there is them giving you three numbers: probability of B, the conditional probability of A given B, and the probability of the intersection. Compare them and then see if they equal. The other way of dealing with testing for independence is when you're checking a product. You're checking that the product of two things is equal to something else. I'm going to tell you the rule first, and then we'll see if I can help you make sense of it. It's not that hard a rule to just simply memorize, right? Uh, so, but understanding where it comes from will help. It'll also help you connect these two formulas together. When we want to check a product, this is what we do. We simply check that the probability of A intersect B is the product of the separate probabilities, right? If it is equal, and it isn't always, right? Probability of A times probability of B is not always the probability of A given B. Let's see, let's think about, you've seen the example of how in males, color blindness is much more common than females, right? So what's the probability of female and colorblind, right? That's the left-hand side. They told us only a very small proportion of women, less than 1% of women, are colorblind, and about half the population is women, so less than 0.5% of the population, right, are colorblind women. That's the intersection. Very small amount of women are colorblind. So A intersect B, very small. The probability of female and colorblind, very small. But the probability of A, right, female, that's 1/2. The probability of B, colorblind, in the general population is more like 2%. So if you don't know anything about gender, colorblind is around 2%, right? If you don't know anything about colorblind, probability of female is around 50%. 50% times, right? There's that product. 50% times 2% is 1%, right? About half women here times about 2% of the whole population is colorblind. That's 1%. On the other hand, we know that over here, out of all people, much less than 1%, much less than 1% is colorblind. In fact, we could almost guarantee it's much less than 0.5%, because remember, women are colorblind less than 1% of the time, and women are half the population. So colorblindness is less than 0.5% in reality. Sorry, colorblindness of sorry about that. Less than 0.5% of the population is both female and colorblind. That's the intersection. But the probability of female times the probability of colorblind is 1%. These are not equal. So colorblindness is not independent. In other words, colorblindness is dependent on gender. When the product is equal, then you know the two things are independent. My favorite example is there is no magic in dice and coins, right? You see what I'm drawing here? 6 results. I've got my heads or tails. There's my coin. And then I've got my 1, 2, 3, 4, 5, 6 for rolling my die. And I'm asking like, hey, what's the chance? What's the chance here? What's the probability over here in the corner? What's the chance of tails and 6? right? What's the chance of tails and 6? Well, look, it's a fair die and a fair coin. So look, I just listed 12 possible outcomes, right? Tails with 1 through 6, heads with 1 through 6. You can see in the chart. I could fill it in with the names of each. 12 different possibilities, and everything is equally likely because the coin and the die are both fair. So I can just go, oh, 1 out of 12, right? The probability of getting that's 1 out of 12 because everything's fair. So all 12 of the possible results have to be equal. 1/12, that's the answer, right? 1/12, right? That's tails and 6, the intersection, right? Probability of a tail and a 6 is 1/12. Why? Because the die and the coin are both fair. So there are 12 results, and everything is equally likely when things are fair. So there's a 1/12 chance. Well, it's not a coincidence, right? That 1/12 is the answer. The probability of a tail, right? Probability of a tail, well, that's a half. And the probability of a 6, well, there's 6 possible outcomes there. Let's check the product, right? 1/12 times 1/6. Yeah, that's equal. Check mark. We do have independence when we have a coin and a die. There's no magical influence, right? Flipping a tails on the coin does not change the probability of the die getting a 6. There's no magical connection between the two. So of course, common sense says, yes, that's a completely independent event. All you need to do is check the product of the two separate events. If it equals the intersection, then you know the two events don't influence each other. If they don't equal, then one of the then the events are related to each other, right? Gender does affect color blindness, so the product doesn't work out. Rolling a tails does not affect the chance of getting a 6, so you can figure it out as 1 in 12 or 1/2 times 1/6. The product does give you the right answer. Now, this is all theory-ish, right? We've got two equations to check. We need to check whether to review, we want to check whether the conditional probability and the regular probability are the same, right? Or we want to check whether the product of the two separate probabilities is equal to the product of the intersection. Well, which one do you do? And the answer there is kind of simple. You do the one that you can because they're going to give you limited information in the problem. Let me go to the next slide. I'm going to snip in, I'll just use the item from the pre-assessment, and we can take a look at that and think of variations to it. Pardon me, I didn't have it ready. I'll snip it in just a moment. Somewhere towards the end of the pre-assessment. So, okay, we got some facts about Dalmatians and blue eyes, and we have that question. Hey, is having blue eyes independent of being deaf? Having blue eyes, independent of being deaf. Okay, so now we have two events. We have the blue-eyed event, and we have the deaf event, and we want to know, are they independent? Well, the question will be, are we going to be comparing a conditional probability to a probability without conditions? Or are we going to be comparing the product of two things, the product of the two probabilities, with the intersection? I don't know yet because I haven't even read the prompts. Let's just do B and D and realize, oh, they'll either give me a conditional or they'll give me the intersection, and I'll know which rule to follow. So let's read the first fact. 31% of all Dalmatians have blue eyes. Okay, that's what I call the unconditional probability. The probability of blue eyes, probability of B is 0.31, right? No conditions involved. Second fact, 38% of all Dalmatians are deaf. That's also a probability without conditions. That's just probability of D equals 0.38. And then finally, let's see what fact they gave us to check against. 22% of all Dalmatians are blue-eyed and deaf. Blue-eyed and deaf. Oh, that's B intersect D. That's what blue-eyed and deaf are. Blue-eyed and deaf, they're both. And the probability of that is 0.22. So what do we have? We have the probability of an event. We have the probability of another event. And we have the probability of the intersection of those events. And we're being asked, are they independent? Very simple. We have one and the other and their intersection. We simply check the product. So this becomes, right, answering the question becomes checking if the probability of B times the probability of D is equal to, I'll put a question mark, I'll put it in red because it's a real question, right? Is that equal to the probability of B intersect D, right? The second method. Why? Because they gave us the intersection and they gave us the two individuals. That's one way to check. Is the product of the intersection the product of the separate probabilities? And now is when you get out your calculator, probably, or maybe you can just estimate it, right? 0.31 multiplied by 0.38. Is that equal to 0.22? And right, no, it isn't. Check on your calculator. I mean, I'll just sort of rough it for you, right? 0.31 and 0.38 are both near 0.33, which is about a third. So you've got about a third times about a third, so you've got about a ninth. About a ninth. You know, pull out your calculator, you'll get 0.08 or 0.09 or 0.10, something like that, maybe even 0.11, and that's certainly not equal to 0.22. What this means is, right, I'll write it as 0.11. You fix it up later if I got it right. It is not equal to 0.22. So no, they are not independent. And you can also say something more. You're noticing that the intersection is larger than it would have been if they were independent, right? The reality is larger. That means that these two are more likely to be together in a Dalmatian. And that suggests there's probably something possibly genetic, behavioral, something in the environment, probably genetics in this case, that deafness and blindness are perhaps close to each other in their genome. So if they have one of those traits, the other one is more likely. More likely, because the 0.22 is larger than the 0.11. That's not generally what they're going to ask. They're just going to ask, is it independent? But you can actually learn a little bit more than just whether it's independent or not. Um, the other kind, I'm just going to mention it briefly. I wanted to go through one whole example, but the other kind of problem would be something like Um, a very similar prompt. Maybe it's not Dalmatians and it's not blue eyes and it's not deaf. It's just a bunch of characteristics. But instead of giving you, instead of giving you this kind of prompt where they're talking to you about an intersection, right? They give you a different kind of prompt. Now, I just did a little green cross through. I still want you to be able to see that because the prompt will just be subtly different. It'll be the idea of they'll tell you something like, I'll pick a number here. I'll keep it 22%. That'll be fine. 22% of all blue, sorry about that, eyed Dalmatians are deaf. Now, I wanted it on purpose. I'm kind of being a little annoying, right? What I'm doing is blue and deaf come in the sentence in the same order, and there's Dalmatians also, and it's even the same percentage. But what I need you to think about is how do you translate that new statement into probability or conditional probability? 22% of all blue-eyed Dalmatians. I really want you to think about that phrase. Of all blue-eyed Dalmatians, of blue-eyed Dalmatians, right, are deaf. If I know that they have blue eyes, then I know the probability of their deafness is 22%. That's very different than what I crossed off. 22% of all Dalmatians, that's any random Dalmatian, any eye color, any height, any weight, any age, whatever, all of them have both blue-eyed and deaf as traits. That's an intersection question. The green, crossed off green, is the intersection. Read this carefully. 22% of all blue-eyed Dalmatians. Oh, suddenly I have a condition. Blue-eyed Dalmatians. So when I write the probability, when I write this in probability, I have to immediately go, oh, I'm being given the condition, right, that the Dalmatian is blue-eyed. So I say given B, right? Given blue-eyed, the probability of being deaf is 22%, right? Probability of deafness given blue eyes is 22%, right? So there's the probability of deafness conditional on blue-eyedness, 22%. And look at these two facts up here, right? This one is the one that we want to look at because this is the probability without conditions, what I've been calling the unconditional probability of deafness. This says the probability of deafness under no listed conditions is equal to 38%. Well, guess what? The conditional probability and the probability without conditions of the same event, being deaf, are not equal. And that means not independent. I'm saying this all very slowly and emphasizing it because in some way it's totally obvious, but in another way you've got to do a lot of translating and thinking, especially if you want to deal with the symbolic nature of it. And you do, because they'll vary between giving you a conditional probability at the end or giving you an intersection. You've got to check whether two things are equal or check whether a product is or is not equal to a third. This one is the simpler. They gave you a conditional fact and you just check it against a conditional fact about the probability of something under a condition. Well, go check the regular probability of that same something, the event, right? What's the chance of deafness as the event? 38%. Well, if they're blue-eyed, what's the chance of deafness? 22%. Oh my goodness. So this kind of Dalmatian, if I know it's a blue-eyed Dalmatian, there's only a small 22% chance of being deaf, whereas a ton of regular Dalmatians of any kind, 38% are deaf. So this problem is saying, hey, if you know it has blue eyes, this Dalmatian is less likely to be deaf than a random Dalmatian that you know nothing about. Random Dalmatian picked out of all Dalmatians, 38% deaf. But now you look in their eyes, you look at all the blue ones, you put them to the side, you grab a blue one, oh, only a 22% chance of deafness there, right? The data here is saying if you know they have blue eyes, they're less likely to be deaf. Again, that's a little bit of extra interpretation. All we care about is knowing that 38%, 22% are not the same number. That's it. That would be the reasoning that you would give in a multiple choice item. Just like over here, you give some reasoning, right? The product 0.31 times 0.38 is not 0.22. It might be phrased differently. Remember, the conditional probability formula is written as a fraction. So it might just be written with, the 0.31 is not 0.22 over 0.38, right? So it might be written with this, sorry, let me use a different color. It might be written as, 0.22 over 0.38 is not equal to 0.31. All I did is I rewrote this equation where I put this as a fraction, right? I just moved it down there, divided both sides of the equation, right? So this is an equally valid justification that they're not independent. And of course, the 3.1 and the 3.8 could have been swapped around. And that would also be a good justification that they're not independent. That's just in case the multiple choice looks a little strange, right? It's not always going to be just, is this times that equal that? No, you'll have to go through some reasoning. And this times that equals that? No is also answered by that divided by one of these is not the third. Yeah, that checking that that's not true is also a way. Just an arithmetic variation, not a change in reasoning.